all data is generated by processes, and these processes in turn are expressions of the underlying phenomena that you are investigating. Now, luckily, this does not mean that there are as many distributions as there are phenomena in the world. In fact, in the second chapter, I already teased that there are many different underlying processes that nonetheless produce data that is distributed according to very similar patterns. For instance, household incomes, population sizes, and earthquake magnitudes are all distributed according to a very similar pattern. However, this pattern is then notably different from other data sets, such as the weight or IQ of people, or even the fluctuations in the stock market. Now, for the most common distributions, mathematicians have developed approximating theoretical functions, which by themselves are described by formulas, in the same way that we saw that the normal distribution is approximated by this bell-shaped probability density function. And also this function had a formula describing it. Now, with these formulas at hand, we can very easily abstract expected properties of our distribution. For instance, the mean, the variance, and the skewness. Now, a powerful skill to have as a data scientist is to be able to identify these types of distributions based on the processes that generate their data. And by doing so, you can have a set of properties to which you can compare the actual properties of this data. And if you see some discrepancies, then you know that you have some peculiarities that deserve some extra attention. Now, in this lesson, we will travel through a distribution zoo, looking at the most common distribution functions, looking at the parameters that they require, and what we can learn from their distribution functions. Of course, we will also discuss some real-life scenarios and applications where you might encounter these distributions. And for each of these distributions, there will be Python code that generates populations according to these functions. So let's get into it. And we're going to start with the normal distribution. Now, I know we weren't going to discuss the normal distribution, but it's just a good introduction to see the structure of how we're going to look at these further distribution functions. So the parameters that define the shape of the normal distribution are the mean and the variance. And some examples are the height of people, or even trees within a forest, IQ, or even throwing darts at a dartboard. But also, if you have a transparent jar of marbles and you let people guess how many marbles are in the jar, then the guesses will be normally distributed. And something very interesting is that the mean of this normal distribution will be very close to the actual number of marbles in this jar. And this is also collectively known as the wisdom of the crowds. Now, if we actually look at the shape of our distribution function, then we of course see this very familiar bell-shaped curve. And if we look at the corresponding cumulative distribution function, then we have this smooth S function. Now, a good heuristic to look at the CDF is to look at its slope. Where the slope is very low, so it's very horizontal, such as at the extreme ends, there is a lot less data than where the slope is at its steepest. And this makes sense because this middle part of the CDF corresponds to the middle part of our histogram, and therefore it's where all of the data actually lies. We see that the 60% data interval, namely between percentile 20 and percentile 80, is symmetrically distributed around the mean of our distribution. And this is basically it for the normal distribution. Now, before we go to the next distributions, let's first look at the code that actually generates these figures. And this brings us to this notebook cell, where we immediately see that we import some new functions, always from scipy.stats. We have comfrec, which we will get to later, but then the interesting part is that from this scipy.stats, we import different distribution functions. We have norm for the normal distribution, uniform distribution, exponential, Poisson, binomial distribution, and Rayleigh distribution. Now, for each of them, we will generate a random set of data, and these will be our populations, in the same way that we generated normal distributions throughout this entire course. Now, the sample size for each distribution is defined at the top. In this case, I took a quite small sample size of 150 just to show the difference between an empirically collected dataset, which is oftentimes around this size, and the theoretical counterpart. Of course, if you make this number much larger, then the empirical collected dataset or generated dataset will converge towards the theoretical curves. But let's just leave it at 150 for now. Now for the normal distribution, what we first do is we define our two parameters, mean 0, standard deviation 0.5, and we generate in the same way numpy.random.normal, and we give it the parameters. Now if we run this cell and we scroll down all of the other distribution functions, then we see that we indeed find the graphs that we had in the slides. So let's then go back to the slides and look at the first new distribution function.